Welcome to the CopperSpice YouTube channel, and thanks for joining us. In this video, we are going to talk about the origin and evolution of auto. Auto is not a data type. It was stunning for us to discover that auto was not actually a new keyword added in C++11. It turns out that auto has a long history, dating back about 50 years. It was added in C and then carried over to C++. To understand the transformation, we need to go back and look at how auto was originally defined and how it evolved in more recent versions of C++. We are also going to show how the usage of auto has been expanded in constructs like a range-based for loop, structured binding declarations, and Lambda expressions. Our last example will examine one of the newer features of C++, called constrained auto.
So what is the definition of auto in C? First of all, it is a keyword, which means it's defined by the language, and users cannot alter the definition. Auto is used to say that a variable has a property called automatic storage. This is a computer science term used to mean storage which is allocated when a function starts and is released when the function exits. In most modern computer languages, we call this a local variable. If you go back to before the days of C, in the language called B, then declaring something as having automatic storage meant something. But by the time C was released, the auto keyword was redundant and unnecessary. C++ adopted the meaning from C, so once again it was carried over for backward compatibility. If you are using a C++ compiler in pre-C++11 mode, then declaring a variable as auto is allowed, but does nothing. All local variables will have automatic storage by default. In C++11, the keyword auto was given an entirely new meaning. Although developers cannot redefine language keywords, there is nothing prohibiting the standard committee from making this change. This can be viewed as a breaking change to C++, but we're not convinced many people noticed. Auto has remained a keyword, but the new definition instructs the compiler to deduce a data type. Auto can only be used in locations where a concrete data type would normally appear. It can be viewed as a wildcard or placeholder for the data type. It is important to understand that auto is not a universal data type, and in fact does not define a type. This is why it has no meaning to cast a value to auto or ask for the size of an auto. One of the most commonly accepted uses for auto is when declaring a variable with a complex or verbose data type, like an iterator for a container. When declaring a variable using auto, you must provide an initial value. The data type of var a will be deduced by the compiler as int. In our second example, var b will be deduced as an unsigned int, where the u indicates the compiler should generate an unsigned value. The data type of var c will be deduced as pointer to int. Even though there is no visible star in this declaration, var c really is a pointer because of the new. It is legal to add a star in the declaration of var c, but it will not change anything about the example. In C++20, the language was expanded so auto can be used in more places. When declaring a function or method parameter, it is now valid to use auto in place of a specific data type. The declaration of function doThing is called an abbreviated function template. Our last example is a bit tangled. Prior to C++11, the only storage class specifiers were auto and static. As we mentioned, auto meant automatic storage, and static meant static storage. They could never be used at the same time, since they mean opposite things. Starting with C++11, the definition of auto changed. It no longer specifies a storage class. It is now perfectly legal to have a declaration which uses both the static and auto keywords. The static indicates a storage class, and auto indicates type deduction.
In these examples, we want to look at how overload resolution is affected by the use of auto. What happens when we call doThing and pass a string literal of quote apple? In the first example, let's assume that only the overloads A and B are visible. The intent of this code was probably to have the string literal converted to an std string and passed to overload A. But since overload B was declared with auto, the compiler will deduce the type to const char star. This is a better match for the string literal than the std string in overload A. That means that overload B will be selected. In the second example, if all three overloads are in scope, it gets a bit worse. Using T for var3 was valid as of C++98. Using auto to declare the type for var2 only became valid as of C++20. Both overload B and C are template functions. Some compilers will accurately report that declaration C is a redefinition of B. But even if the declarations are allowed, trying to call this overload set will produce a compile error saying ambiguous overload. Using concrete data types or opting for auto, this can be a very heated conversation, and it's usually a personal choice. But in our opinion, there are places where auto can significantly improve code readability and should always be used. Let's talk about the case where we're looping over a container where the element type is very long and complex. In this exaggerated example, each element is a tuple containing a string and a shared pointer to a map. Using auto for the iterator type is easier and less error-prone. But now we have something new to consider, since there are three different ways to modify auto with various qualifiers. In the first case, item A will be a copy of the element, and copying can be quite expensive. In the second example, the code is looping by L-value reference. This means the body of the loop can modify the elements in place. You should be careful with this option if modifications to the data were not intended. Typically, a const reference is the best form to use. In this case, no copy will occur, and any modifications to the elements of the container will be reported as a compile error. The structured binding syntax was introduced in C++17, which makes it easier to work with compound types. Code which returns something like a pair, a tuple, or an array will be associated with the names listed in the structured binding declaration. Due to the wording in the standard, structured bindings do not technically create variables. So in C++17, X and Y cannot be captured in the capture list of a Lambda expression. As of C++20, the definition of Lambda expressions was changed to allow capturing structured bindings. It is important to remember the names listed in a structured binding are still not variables. On line 1, the return type of some function is a pair containing an int and a string. The code on line 5 is a structured binding declaration, and after the code is executed, the names x and y refer to the first and second elements of the pair. It may not be obvious, but it is essential to understand this next point. The use of auto in a structured binding declaration is required. In this one place, auto is not just a keyword. It is a specifier, which means auto is no longer acting as a wildcard. Even if both elements of the pair were the same concrete type, it is not legal to use the actual data type. The specifier auto must appear at the beginning of a structured binding declaration, and the compiler must be allowed to deduce the data type of each binding.
Another place where auto appears is in the declaration of a lambda expression. Both of these examples use the keyword auto to deduce the data type of a variable. The auto highlighted in yellow is the data type of the lambda expression. You could use std function, but this is not necessarily the best choice. The auto highlighted in purple is part of the parameter declaration and transforms this line of code into a generic lambda expression. The data type for var1 will be deduced by the compiler when mylambda a is called. Generic lambda expressions were added in C++ 14. On the last line, there is a T highlighted in purple. This syntax was added in C++ 20. We refer to this style of declaration as a template lambda expression, although some may regard this as simply another generic lambda expression. The difference between these two declarations is that in our template lambda expression, the deduced type has been named T, so it can be used in the body. As shown in the prior slide, a template lambda expression does not start with the word template. It is a lambda expression that uses type name T before the parameter list. This can be confusing, so let's walk through a few more examples, starting with the declaration for doThing A, which is a normal function. To declare a normal template function, we simply add a template argument list before the declaration. When doThing B is called, the data type can be passed inside the angle brackets, as shown in the comment. It is important to mention that passing the type is optional, since it can be deduced. The third example is a normal lambda expression. This is the tricky part. In the declaration of example D, we can add a template argument list before the declaration of the lambda expression. However, this code is not declaring a template lambda expression. Instead, it declares a variable template. The code on the last line, highlighted in purple, shows how you read a variable template. For clarity, the variable name is mylambda_d. The data type used with mylambda_d must be specified in the angle brackets and is not optional. In this example, the type is int, which means the data passed to the lambda expression must be convertible to int, but this type will not be deduced.
A new usage was added in C++ 20, which permits specifying type constraints preceding the word auto. The type constraint, which appears before auto, must be the name of an existing concept. It can be a concept defined in the C++ standard, or one which was defined in your source code. Although the terms sound similar, a type constraint is not the same as a constraint. A constraint is used as part of a requires clause and is not associated with constrained auto. When you are referring to a constrained autotype specifier, the definition uses the term type constraint, and this is one place developers should not omit the word type. When calling the function doThingA, the type for var A must meet the specified constraint. In this declaration, var1 must be a data type which is copyable. This could be a primitive type like int or a class like stdstring. Trying to pass a non-copyable type like a unique pointer will result in a compile error. If you're calling doThingB, the type of var2 can be any data type which inherits from the class fruit. In a fruit-like inheritance relationship, the data type for var2 might be orange or banana. It is pretty amazing that one simple word like auto has evolved from a storage class, wildcard, indication of a generic Lambda expression, variable template, and now we have constrained auto. Spoiler alert, it appears the Standard Committee is going to add even more auto in C++23.
For more information about the CopperSpice project, please visit our website at www.copperspice.com.
Thanks for watching. We hope you found the content of value. If you have any questions or feedback, feel free to leave a comment on this video or send us an email.
Please make sure you subscribe to our YouTube channel and come back for our next video.